Hi everyone, thank you for watching this video. Today we're going to be discussing the topic of IR and NMR. So let me go ahead and switch over here to our lab manual. After reviewing this, I'll go through the modules that we'll need to complete. So that would be the pre-lab that I would assume that you completed before this. Additionally, with the post-lab questions that need to be completed afterwards. And as well, going through the lab manual, I will target the post-lab questions in order for you to know what to complete in your lab manual. So firstly, today, we're going to be discussing infrared absorption spectroscopy, which is also known as IR spectroscopy. And within this unit, we need to know that IR spectroscopy is the amount of radiation absorbed by compounds within the infrared region of the electromagnetic spectrum. So we know there is a full electromagnetic spectrum of light waves that are from a small amount of energy all the way up to a large amount of energy. But in this instance, we're only going to be looking at the infrared region, and this would be in the area of the wavelengths between 2.5 and 15 micrometers. And in this instance, we should know that 1 micrometer is equal to 1 micron, which is 10 to the negative 6 meter. And this corresponds to the frequencies between 4,000 and 650 inverse centimeters. Additionally, I want you to know that in IR spectroscopy, there is an inverse relationship in terms of the scale whenever we look at an IR spectra. So on the left-hand side, it'll be a very large number, such as 4,000 in this instance. Going to the right, the number reduces down to 650. So instead of it being a scale from 0 to 100, just think of the scales flipped in this case, and it's going to go between 4,000 down to 650. And so the inverse centimeters, which is also known as reciprocal centimeters or wave numbers, is the way that we will describe this unit. And so here you can see that frequency is equivalent to 1 over the wavelength in centimeters, or 10,000 over the wavelength in micrometers. And you can see here this V is also known as frequency, and then addition this lambda is known as wavelength below here in micrometers, which would be 10,000 divided by the given frequency. Now, we won't really necessarily be needing to know how to interconvert these numbers, because when we look at an IR spectra, we're going to be more so focusing on the location of specific frequencies that we'd be seeing on the spectra itself. And we would see this indicated by broad peaks, sharp peaks, and we'll see many examples going forward, such that you can actually look at a spectra and say, okay, I see here at the 3,000 mark, we have a very broad peak, for instance, that would indicate to us an alcohol group would be present. So that's just a brief preview to you to know that these are some information given by the lab manual, but it won't be as relevant as it will be to understand where on a spectra that you would see specific wave numbers. So going forward, as a little bit of a precursor, is that when electromagnetic radiation in the infrared region is absorbed by molecules, the molecules are excited to a higher energy state, and this can be on the order of 2 to 10 kcal per mole. And in this instance, whenever we observe this excited energy state, we will see a type of mode of vibration of the atoms and the position of the peak. So again, when I was referring to the specific wave number, that will tell us the position of the peak. The mode will vary between stretching, bending, vibrating, etc. And we'll go forward to note exactly where each of these occur, depending on the specific functional group that we may be looking at for the day. So the intensity of the absorbance is proportional to the change in the dipole moment for motion. So for instance, in here, this carbonyl stretch, the C double bonded O stretch, will be much more intense than an alkene stretch, because there's a dipole moment going from the carbon to the oxygen. So going forward, by the use of this information, the presence or absence of certain functional groups or the structural features of a new compound can be determined. And so once again, once we look at the spectras that we'll be seeing down once we get through this text, then you'll understand more of the specific functional groups we can find at specific locations given on an IR spectra. So another important background information is that the masses of the atoms that are involved in the vibration, specifically the stronger the bond and the lighter the atoms, refers to a higher amount of vibration frequency. And additionally, we should also note that the bending motions are easier than the stretching motions, and so the former absorbs at lower frequencies. So we would observe the bending motions being at lower frequencies. So what does this exactly mean? So in this right here is a great example. So symmetric and asymmetric stretching, they are at a higher frequency here. So around 2.8 thousand inverse centimeters and 2.9 thousand inverse centimeters. Whereas when we see the bending or the rocking motions, this is more down in the fingerprint region, and we'll discuss that further, what that exactly means. But it is a lower, so you see that they absorb at lower frequencies because they are less difficult for the molecule, functional group, or compound in order to perform this bending or rocking. It's much easier than for it to be stretching. The stretching is a much higher energy, therefore the amount of inverse centimeters would be a larger number. So going forward, now in order to explain what I was talking about with the fingerprint region, etc., we should note that there are certain specific areas in an IR spectra that are important for us to analyze. And so they divide it into two portions in this situation here. So the region 4000 to the 1500 region is useful for the identification of various functional groups, like I had spoken of before, the alcohol. Maybe we can see an alkene group, some nitriles, and we'll go through each of these and target the specific wave numbers later. But the thing of the fingerprint region that I was speaking of, that's going to be from 1,500 to 600 inverse centimeters. And you'll find some very unique patterns down in the fingerprint region when you're looking at a spectra. And those will be very helpful for us in order to either analyze a random graph that was given to us, a specific spectra, and you want to just look at it and try to analyze it for yourself. Or if you're running an analysis of a compound that maybe you made in a lab, and then you want to say, okay, good, now did I actually attach an alcohol group to my compound? Okay, let's run it and see if we can find that in our unique pattern on our spectra. So here are some very important frequencies that should be noted, and you will want to memorize the very important things in very specific locations. Some of them will be very general and stay near each other, but there are some specific ones you really will want to memorize. So for instance, here in the 3600 to 2700, you'll notice halogen bound to a hydrogen will perform a single bond stretching. As I said before, an alcohol, possibly an amine, carbon to a hydrogen. And again, like carbon to hydrogen, that's very generic. That could be within anything. But so with something like a phenol or an alcohol, you would notice something very different, very broad peak on your graph. And then going forward, 3,300 to 2,500, hydrogen bonded OH bound to halogen stretching, an ammonium ion. Then going even lower, you would see the triple bond, multiple triple bonds here, or even here where you have a double bonded nitrogen to a carbon followed by another double bond. And then once you even go lower, then you're going down more into the double bonds region now, where you just have your carbonyls, your carbon double bond to nitrogens, or your alkenes with carbon-carbon bond. And then finally going even lower, you're down to the single bonds region, where you'll see your amines, your methane, possibly carbons interconnected. And once again, this is where I was saying that sometimes it gets a little bit more ambiguous because when you have single bonds, when you have a giant compound with multiple single bonds, the 1600 to the 650 region can be less informative because you're just going to have so many of those bonds in most compounds that it won't be as relevant as it would be, if you had one triple bond, then you would know you need to look, within this region specifically. And if you don't see anything there, then you have a problem. And that's why an IR spectra is important to analyze, because these things will show for any sort of compound that has specific groups on it. So it's very important in order to analyze functional groups whenever you are performing an IR spectra. And the way that we perform IR analysis is through the FTIR, which is Fourier transform infrared spectroscopy. And what happens is that an electromagnetic radiation splits into two beams, and one travels a longer path than the other. And what happens is that this goes through the compound and it actually recombines at the end and creates an interference pattern or an interferogram. And then through mathematical manipulation, which in this instance, if you ever do run an IR, you would be running it on a software, and the software will run that mathematical manipulation, which would be the Fourier transform, on the interference pattern that you receive, and then you would be given your nice IR spectra for you to analyze. So fortunately, we have technology now that performs this for us after we prepare our sample, and then the machine will run this for us. So I didn't highlight this, but I'm going to go ahead and put this here as well. All of these are very important things for you to know. And it's good for you to just memorize the very important ones here, because certain ones like alkane stretches, it's kind of the same situation I spoke of before, where you're going to have a lot of alkane stretches in almost every single compound, unless it has no alkanes, which will be very rare when we're looking at organics. And so you would want to look at more important things like carboxylic acids, the location here, amines, aldehydes. Those are more unique functional groups that are only on specific compounds. So if you're comparing, an aldehyde to a carboxylic acid, you would note that there would be a very significantly different IR spectra to be looked at in this instance. Even going down into the nitriles region, it's a very small region right here. So that would be an important region to memorize for you whenever if you looked at a random IR spectra given to you and you saw something between 2200 and closer to 2300 in between that range, that's very indicative of a nitrile, because as you can see here, the others, they don't really interfere in that area. The alkynes slightly do. However, nitriles and alkynes, they're very similar. They're both triple bonds, and those are the more important ones that need to be memorized, because those are so unique. You will not normally find that in just random compounds that do not have triple bonds. So that's a good thing. They would just be flat, maybe just very light interference, from the background. But this will be very obvious on a graph when you have a nitrile with a very significant peak. So please go through and make a list and then understand, like I said, with the alkanes, what is more common in all compounds that you look at and what is more uncommon, like the nitrile example. And then once you've done that, then you have a good clear path of what you need to know precisely to memorize. Because if you have interfering patterns that are in the same region, it's not very clear or helpful to look at it and say that you can make a clear, distinct analysis of a given compound, in the sense that if you say that it's at a specific wave number and then there's 3 other sorts of functional groups that are at that wave number, that's not a good indicator for you, because you may be incorrect, because there's a possibility of, in that instance, 3 other functional groups that maybe are peaking there. So memorize the unique ones, such as the nitrile, for instance, that I gave as an example. And make sure to go through and understand the generality of where the other areas should be as well. So a good part of this lab manual that will easily break this down for you, that will still need to be memorized in a sense for the unique spots, is that we will now break down into the specific functional groups, such that firstly, alkanes, we would notice stretching frequencies with a strong. So when they say strong, that just means a very deep peak, very, very deep valley in this instance, because it's going down on all these spectras like here. So you would see a strong stretching frequency here from 3000 to 2800. Additionally, any aliphatic carbon-hydrogen bonds you would see in that region. And so for the bending mode of an alkane would be more near the 1470 to 1420 and 1340 to 1380 regions. And so you can also look in those little regions on your spectra to know, do you have alkanes from your compound? And then finally, you can additionally find the carbon-carbon stretching vibrations in the 1300 to 1100 region. And once again, once you go lower, it's a little harder for you to know if those are a good thing to analyze, because that can overlap with other things once you get closer to the fingerprint region. Now, only specific, very small things in the fingerprint region will be important for you to memorize, and such that here, if you have a sort of ortho, meta, para, substituted benzenes, they're very unique in the fingerprint region, whereas the alkanes can be more general. So going forward, olefinic, and I put a note here, that just means alkenes. So alkene carbon-hydrogen stretching peaks generally are around 3,100 to 3,000. So it's going to be a little higher here than the alkane. And in this instance, that would be the stretching peak. So remember, that's stretching. So next, if we want to talk about the bending, now it's going to be a lower energy requirement, right? So the bending of the out-of-plane vibrations are going to be in the 1,000 to 650 region. And you can see that here on the spectra right here. It's near between those two. You have an alkene bond with a pretty strong peak there. That's pretty obvious. Whenever we say strong, you can see this very deep peak here. And we would say it's weak if you're talking about peaks, like in this instance, between 1,000 and 1,200. It's a very small little, maybe a little bump here and there. But in these analysis, you can see they go very deep, and that's very significant for us to clarify that's a very strong functional group there. And so finally, after this, in this fingerprint region, then we will talk about this other part of the carbon-carbon double bond, the alkene stretching frequency, as well in the 1,600 to 1,675 region. And you can see that here with a tri-substituted carbon, where it's bound to two other groups, and then you have your alkene here, and that is indicative here in this 1,600 to 1,675 region. Here is our alkane here between our 1,400 to 1,600. So that's much different than our alkene in this instance. It got shifted more, in this case, let's say upfield. And then we have this, we have a cyclohexane ring with an alkene bound here. This can also be within this region. I think that this is actually referring possibly over to here. It's kind of a poor image right here. So let's go ahead and move past that. We can say the alkane here in the higher of the 2,800 to 3,000 region, as they were speaking of here. And then finally, the alkene is even higher because it's a higher required energy for this stretching. So the stretching is, it requires a lot of energy for it to perform stretching, whereas the bending modes, the out-of-plane vibrations that they're talking about, the bending, as we spoke of in the theory, it requires less energy. So it would be a much lower, close to the fingerprint region in this instance. And the stretching peaks, those will be always higher, maybe in the, there's a little bit of the stretching here in the 1,600 region, but mostly with the stretches that we see that are very high energy, you'll see them close to the 3,000 region. So going forward, we have here the alkynes, and this carbon-hydrogen stretching vibration of terminal acetylenes. So a terminal alkyne in this case is going to be even higher because, it's an alkyne. It's going to require even higher energy to perform that stretching. And so that would be all the way up in the 3,300 region. So that's a very significant thing to note. The alkynes, their highest stretching is very high, 3,300. Then you have your alkenes closer to 3,000, and then you have your alkanes in the 3,000 region and a little lower to 2,800 and such. So that's a very distinct thing that you need to memorize in your mind, is that the higher energy requirements, the deeper into the wave numbers, the larger wave numbers that are going to be required in this. And then also in this instance, it's the inverse relationship. The higher numbers on the left, the lower numbers are all the way on the right. So then also a strong band, as we discussed before. Secondly, the alkyne stretching band additionally can be found in the 2150 region to 2100 region. And again, now this is not a terminal alkyne. The one we're talking about here, as you can see as a good example, this is a alkyne that would be in between two other, functional groups. Maybe you have a carbon chain, and in between you have an alkyne. That's why you would have here in the 2000 region. Versus a terminal alkyne, it's very hard for that to stretch. It requires a lot of energy to excite that. So that's why it's so much higher. Then, and this is if it's monosubstituted in this like 2100 to 2150. But if it's di-substituted, this comes to a more a harder to move alkyne, if you think about it, it requires more energy for that to actually stretch if you have more things substituted with the alkyne. So in the case of it's di-substituted, then it would be a little bit higher in energy. And in this case, they don't have that specific peak. So, we'll use this mono-substituted situation as an example. But if we did, it would be a little higher than the peak given here. And so finally, if we had a polarizing substituent, like an alcohol that's nearby an alkyne, then we could see a partial peak over at the 1600 region. And this is a sort of an example here. It's not a very good example because this is more so showing an carbonyl. But I would be more focused on the specifics with the alkynes, very far past 3000, like 3200, 3300 over here. And then also the possible stretching band in the 2000s region. But honestly, for alkynes, my personal go-to is near 3300 because that's pretty much next to and past the alcohol peak. Additionally, it's further than the alkene peak, as we spoke of before. And those are like the specific things you want to memorize in your head of those unique numbers where you can find these functional groups. So going forward into larger compounds, so such as an aromatic ring like a benzene, you would see a carbon-hydrogen stretching, and it's so stable that it really doesn't want to perform that. But we can still see that this does perform in the 3100 to 3000 inverse centimeters range. Whereas also we can see some out-of-plane bending, not stretching, but remember bending, very low energy requirement in the 900 to 690 region. Those are usually, very slightly analyzable. There'll be peaks like this. The thing is that the fingerprint region starts to slide off because we're leaving the IR area. So when you start going towards that, smaller wave numbers, then you're leaving the infrared area of the electromagnetic spectrum. And so that's why the spectrum starts to kind of slip off, because now it's going, in a sense, towards infinity, because you're now measuring very, very small numbers. So the most important thing, in my opinion, to remember for aromatics is in the 3000 to 3100 region. But other significant things we can look at would be sharp peaks at around 1600 and 1500 inverse centimeters. And yeah, so, here's some nitro groups as well here attached into our benzene ring in these areas. This is not a very good image. I would also recommend, if you have any significant difficulties understanding where any of these spectras are, as this is an older lab manual, I would recommend to Google an IR spectra of a specific functional group you're trying to find. And Google has a library. There's just vast libraries of analysis of thousands and thousands of molecules and compounds that you can look at. And Google is an amazing resource for anyone to sort of study any sort of these chemical topics, because some of these things can get unique and there may not be something in your textbook that can help you with those. So I would definitely recommend to look it up if you need to know a specific functional group or want to see an example of it. And so the big one that I liked to discuss in this instance for the alcohols, phenols, and enols, the OH stretching, very, very high. Remember also the dipole moment is so significantly high in this instance, and that's why it requires such a high energy from the 3650 to 3600 region. And also it can also broaden. It's very broad. This is a very unique characteristic of alcohols, is instead of it being a very sharp peak, very strong and sharp, it's very broad and strong. But it's the big thing, you'll see a very large, broad peak versus where you see sharp peaks for most of the other graphs or other functional groups. And so additionally, intramolecular hydrogen bonding to carbonyl or nitro groups as an enols would lower it. So in that case, it would be shifting more towards the 3000 range. And again, this is where it starts to overlap with other alkenes, alkanes, alkynes. And that's why it becomes a little ambiguous with certain compounds as to analyzing, if you have an alkyne, whenever you have a massive phenol peak here. And so other specific ones that you can look at for these as well will be strong bands from bending. Remember, the bending of that is a very easy mode. and possible carbon-oxygen stretching, and this would not be carbonyl, carbon-oxygen, like an ether in that instance, or an enol, and that would be in the 1500 to 1300 inverse centimeter and 1200 to 1000 inverse centimeter areas. And those won't be as broad as this alcohol peak will be. So the take home here that I would like to let everyone to know is that main massive peak that you would see from a phenol. It'll be like almost to the 4000. It'll be very strong and very wide. Okay, going forward. So these are the unique ones. Carbonyls, they're really, really great to analyze by IR spectra. However, you have to memorize the locations because it's very unique. Very, very, very unique. They're very close to each other, but like I said, they're very unique. So, the carbonyl stretching of an aldehyde and ketones. So, saturated aldehydes and acyclic ketones are observed at 1735 to 1710 and 1725 to 1700. So you see how unique that's very small. So in this instance, the aldehyde 1735, the ketone 1725, very hard to analyze in that instance if you're trying to separate them. But for instance, aryl aldehyde would be 1700 to 1690, and diaryl ketones would be all the way down to 1670, 1660. So you can actually take these apart and know the differences if you know the substituents attached to your carbonyls. So if you have an aryl aldehyde and instead you have an acyclic ketone, then you would know that you would see the aldehyde over here in the 1690 region, and the acyclic ketone would be over closer above that in the 1700 to 1725 region. So they're very unique. So just make sure that you know the very unique specifics for these carbonyls. And then additionally, there's a stretching vibration from two peaks in the 2850 to 2700 region for aldehydes. And then additionally, a cyclic ketone with a 4 or 5 membered ring. That would be closer to 1780 to 1745. So that's also some specifics that you should remember as well. But mainly, you will want to separate them, especially from here going into this next one of carboxylic acid. So the carboxylic acid, one major thing you would know is that there's a broad peak because of that oxygen, hydrogen, remember, the alcohols, in the 3300 to 2500 region, whereas you can see some carbon-hydrogen stretching occurring from this as little small peaks, which would be here, little very tiny additional ones, but mainly down deep here. And then the carbonyl, so here in this region on this graph, this is where we're looking at for any sort of aldehydes, any sort of ketones, any sort of esters, aldehyde, carboxylic acid, ketones, yeah, like anything in the carbonyls section. And the carbonyl group of a carboxylic acid is at 1730 to 1700, and it is also shifted to 1720 to 1680 by adjacent unsaturation. So if you have an alkene adjacent to your carbonyl, that will shift it down. But otherwise, the carboxylic acids are, slightly a little higher. And but the most characteristic thing with a carboxylic acid would be that additional alcohol group. You won't see that if you have an aldehyde or just a regular ketone, right? Because there's no additional carboxylic acid or alcohol group next to it. So in this instance, this is an infrared spectrum of the aldehydes. So you could see some characteristic peaks here from the aldehyde they were speaking of with regards to the two peaks in this region. So they're not broad like the alcohol, but there's some characteristic peaks. Then you have your carbonyl peak here in this 1700 region. Then here's our carboxylic acid now, right? So carboxylic acid has our deep oxygen-hydrogen stretch, and we also see our carbon stretch here. It adds into the broadness of it. And then the carbonyl peak, very strong and deep here at the 1700 region. So let me see. One moment. All right, now let's go ahead and continue into our carboxylic esters and lactones. And the saturated ester carbonyl stretching will be in the 1750 to 1730 region. And if we have unsaturation adjacent, an alkene adjacent to the carbonyl group, this would lower the frequency by 10 to 15 inverse centimeters. Whereas if you have unsaturation adjacent to the oxygen, the esters, oxygen, such as in the enol and phenol esters, it would increase the frequency by 20 to 30 centimeters, inverse centimeter. So you have to know if there's additional unsaturation with the groups that you're analyzing. So if you were analyzing only a carboxylic ester, it'd be much different than if you were analyzing a carboxylic ester in a compound with adjacent unsaturation, etc. And the carbon-oxygen-carbon stretching of esters appears as two bands in the 1280 to 1050 inverse centimeter region. So you could also look there. The asymmetric stretching peak at 1280 to 1150 inverse centimeters can be additionally found with very strong characteristics. So one good thing that you can analyze for cyclic esters like lactones in order to know whether you have a 5-member or 4-member ring would be to see that a 5-membered ring would be absorbed around 1770 inverse centimeter, whereas a 4-membered ring would be around 1820 inverse centimeter. Okay, so going forward now into anhydrides, an acid anhydride would be known with two high-frequency peaks. These would be at 1830 to 1800 and 1775 to 1740 inverse centimeter peaks. And one good thing I would recommend, this would be a time for flashcards or any sort of an app that could perform sort of flashcard situation. So that way that you can start to memorize where these locations are. And then you can do it by the trial by elimination theory. If you were given an IR spectra and they said, okay, here are the peaks. What do you have in front of you? This way, when you know exactly where the location is, if you see two high frequency peaks at the 1800 and 1700, you would say, oh, that's very characteristic of an anhydride. And you might not know that off the top of your head, but when I recommend these sort of flashcards or any sort of apps that assist with memorizing this, that is the reason I do that, because memorizing this will help you in order to understand and analyze an IR spectra if it was given to you. So going forward into amides and lactams, and amides carbonyl stretching is observed in the 1700 to 1630 region. And additionally, both adjacent unsaturation and ring formation cause it to shift to higher frequencies. So if you do have those characteristics adjacent to your amides, then you would notice it to be closer maybe in the higher carbonyls area, the 1750s or so. And also, we should note that primary and secondary amides show nitrogen-hydrogen stretching in the 3,500 to 3,100 inverse centimeters. That's a very characteristic one that you could see. And also the nitrogen-hydrogen bending at the 1640 to 1550 inverse centimeters region. And then going forward, ethers, the asymmetric carbon-oxygen stretching, it appears in the region of 1280 to 1050 inverse centimeters. And additionally, the phenol and enol ethers absorb at 1275 to 1200, whereas dialkyl ethers absorb at 1150 to 1050 inverse centimeters. Now, epoxides are unique because they are going to be between 1270 to 1240, 950 to 810, and 850 to 750. And so they don't have an image here, but I will jump to a table at a different point to show you more of the ethers and epoxides in that case. But going forward, amines, the primary and secondaries show the nitrogen-hydrogen stretching in the 3,500 to 3,300 inverse centimeters. And they primarily have two bands with approximately 70 inverse centimeters apart due to the asymmetric and symmetric stretching nodes, whereas the secondary amines will only show one band. And it will be in that similar region as well. In general, the intensities of the nitrogen-hydrogen bands are going to be less. They are less polar, additionally, less of a dipole moment, where the N-hydrogen bending and the carbon-nitrogen stretching absorptions are not as strong as the corresponding alcohol bands that would occur, and they will be at approximately 100 centimeters of higher frequency, more energy required for this to occur. So in addition, the amine groups give an additional broadband at 900 to 700 centimeters, so you may be able to see it in a given graph that you would analyze. So here's our amine stretch up here in the upper 3000s, and then you could also see a nice amine bend right there. And then additionally, you can see your carbon nitrogen stretch here, and then here would be an ether stretch in the middle of this. So it depends on what you're looking at. And in this instance, you're looking at a benzene ring with your attached ether adjacent to your amine group as well. So that's why you would additionally see your ether group there. So that's a very small example of it. If you need more examples, like I said, please go online to make sure to look through more of the examples given. So for nitro groups, very, very strong, very specific. They should have had their example that they used up above down here, but that's okay. The asymmetric stretching, it can be appeared at 1560 to 1520 inverse centimeters, and symmetric at 1360 to 1320 inverse centimeters. Then finally, the nitriles that we spoke of before, very sharp, usually strong absorption at 2260 to 2220 inverse centimeters, and that's the specific spot. You're just gonna have to memorize that specific spot. Very important. So now that we've gone through all of the important functional groups, I would like to discuss how, in order to analyze or prepare your samples for running an IR. So in this instance, there is one method for films that we most likely won't be doing. Maybe you will be doing this if you have a sort of career that involves utilizing cellophane, saran wrap, etc. And you would cut a hole, then you would tape the film over a card, and then the card can be placed into a sample beam. Then the beam is shot through the film, and then that would refract into your chromatogram, and then you could go forward in order to analyze your IR spectra. Now, that's not very relevant in terms of what we'd be performing in the lab. That's why I've highlighted this section more. So you'll take a thin film of liquid, in the case that you have a liquid sample, an oil sample, or some sort of a liquid compound. You would take a salt window, and you would want to place a thin film of the liquid in between the transparent windows onto a specific little salt disc. And this gives you an example of how you exactly would prepare the sample, but you basically place it into the holder, and this is the whole salt assembly here, and you would place it in between the two windows in there. You put your liquid sample in there, you put it together, then you put your gaskets on top, and then you would put your plates on there, screw it in. Now it's enclosed, and you have your sample in between a plate. And it's hard for me to explain to you, by words. It'd be better in person, but it's also very simple. You just have to put it in between the windows, and then put all the things together like a sandwich, and then screw the whole plates together. And then afterwards, one important thing to know is that if you do ever run this in lab, make sure to disassemble the cell. Never leave it there for it to crust up and the compound to just be dirty and sit there. Always make sure to clean it. So you rinse the windows well with a dry volatile solvent, DCM, hexane, possibly acetone, anything that would eventually, like volatile, it would evaporate. So that way it doesn't ruin your next spectra going forward. So now solids, this is my preferred method for performing any sort of IR. There are multiple sorts of solid methods. One is a sealed cell for volatile samples or solutions of compounds. So if it's a very volatile sort of a solvent or anything, if you're trying to analyze a solvent in this instance, or a volatile sort of oil or compound, it can be dissolved. In this case, a 10% solution into carbon tetrachloride will not show in the IR spectra. And so it can be placed into a sealed container, little thing, and then that can be placed into a holder, and that can be ran on the machine. This is not as common unless you work possibly in an industry that uses volatiles, and then you would have a specific little container that you would inject your sample into, and then you would run it on the IR, and then the IR spectra would give you your information. The one that my lab uses is this KBR pellet. And so what you do, and this is super, super interesting, super simple too. So you take a dispersion of 1 to 2 milligrams, only a few milligrams of your sample, and then you take your compound, you grind it down with a pestle and mortar into 50 to 100 milligrams of dry potassium bromide powder. And so what it does is it mixes it all in, Potassium bromide won't measure on your IR spectra. It's just like salt. And so then once you've done that, you could use this pellet press. And this is super awesome. So you place your sample into the pellet press, and then you screw the two screws together. And what it does is it actually pressurizes it down into a small little pellet. And once you have that little pellet, you place it into a little holder. And then you take the holder, put it in your IR machine. And then once you put it in there, you close your machine, you run the sample, and then it'll shoot the beams through it. You're done. That's it. You just have to mix together your compound into the dry KBR, and that's it. You make your little pellet. Very easy. You can hold on to the samples as well if your compound is not very, if it doesn't decompose very easily. You can hold on to your pellets, and you can actually like run those again in the future if you prefer. So that's a good thing that is part of the KBR pellet method. So the NuJoul, not my personal preference. However, it is okay to use for certain ones. Some people are, they love the NuJoul method. I don't really prefer it, and I'll explain why going forward. But it is pretty simple. You just take grade mineral oil, which is NuJoul. That's all it is, just mineral oil. And you take a very ground of your solid, 5 milligrams of your very ground solid, and then you place it between salt plates, and then you put a drop of your NuJoul in there, and it disperses your solid into it, kind of, dissolves it, and then you put your salt plate on it. Now, this is the reason I don't prefer it, is because absorption bands will be present at 2850 to 3000, 1460, and 1375. So what you can do is run a background of NuJoul, and that will give you a standardization. But in my opinion, I feel that would take away from any sort of impurities or anything, any sort of background that may be given off from your compound. So that's why I personally do not prefer the NuJoul method and go forward more with the KBR pellet method. So those are a few of our solid methods in order to perform this. And going forward, here are some final footnotes and overviews that you might want to review, some summaries towards the IR spectra. But primarily, I want to go forward to let you know this is exactly the procedure that you'll need to write down in your lab notebook. So make sure that you have all this written down. In this instance, you want to know very, very few things in terms of the sort of glassware and such that we use, because it's not like we're performing any sort of reactions here. This is a very theoretical and analysis-based lab. So we would be putting ethyl benzoate, into a machine in an instance. So finally, these are our post-lab questions here. So make sure to complete these at the end of your lab manual after you've written up your procedure, etc. And then finally, as well, these pre-lab questions should be completed, before the class period. So please make sure to complete these, and then send me an email with these completed. If you've already watched this, then you'll have an easy way to refer to the answers here. And make sure send me a screenshot of this pre-lab questions if you have not done so far. And I'm going to take a quick pause here so that way we can switch over to the Proton NMR. Okay, so now for the Proton section, Proton NMR, 1H NMR, this is going to be important for everyone to go ahead and use additional resources for this. This is an older text, just like the other one. So that way that you can know the specific locations of certain protons that can be analyzed. But the good thing about this older text is that it is more about theory in this instance. So let's go ahead and discuss the specific backgrounds on Proton, and then I'll give you the additional resources that would help you to analyze specific compounds. So firstly, we should know the chemical shift. And this is going to be known as in parts per million. It's going to be on the scale. And just like the IR spectra, it's going to be inverse. So there's going to be larger numbers on the left, smaller numbers on the right. And so going forward, this is going to be parts per million. And it's the numbers of the protons attached to a carbon and a function of the environment of the protons. So within the given environment, it's going to shift the protons in specific ways. And these effects are summarized in table 13.1. So let me see really quick. 13.1. So down here, this is going to be your cheat sheet in a way. You may want to also do sort of flashcards for this, or sort of memorize where specific ones are. And so in this instance, we'll be discussing an alcohol group going down the line. But in this case, you can look here and see where that you have a group attached to it. So in this case, an alkene, alkyne, phenyl group, fluorine, chlorine, bromine, etc. And these are all reference points. And so you can see here from 0 going to 5 parts per million, this is the scale going from right to left. So make sure that you understand whenever you're looking at a spectra where to look at the specific groups for the specific locations of a given compound or a given functional group. So let's go back up here to the top. That's the main part of chemical shift, is the location. Just like in the IR spectra, you had specific wave numbers. The chemical shift, the ppm, that location is going to be that location where a specific proton is attached to a given functional group or compound. So the multiplicity, now this is a good way for you to kind of put the puzzle pieces together, is the number of lines in the signal, and the multiplicity will indicate the adjacent protons to that specific proton that you're analyzing. So if it's a singlet, one line, that means that you have one proton. There's no protons adjacent to it, okay? D, doublet, that means, or two lines, that means that there is at least one adjacent hydrogen next to it, one neighboring partner, okay? Triplet, 3 lines, that means you have at least 2 partners next to it. So it's always your basis plus whatever is next to it, right? So singlet, there's no adjacent protons, it's just that. Doublet, you have 1 adjacent proton, so here's your doublet. Triplet, you have 2 adjacent protons. Quartet, okay, so your hydrogen, and then you have 3 different adjacents, right? So quartet, then there'll be a doublet of doublets. So if you're a proton here and you have 2 hydrogens on this side, 2 hydrogens on this side, and they're symmetric, that would be a doublet of doublets. And then multiplet, if it's just a hydrogen in the middle, you have like 3 on this carbon adjacent, 4 on this carbon, or sorry, well, you can't have 4, it'd be 2 on this carbon adjacent. You have a multiplet, you would see like multiple different little peaks instead of very unique, like singlet, doublet, 2 peaks, triplet, you'd see a 3 peak situation. The multiplet just means any sort of additional 5, 6, 7 numbered of peaks given for this instance. And so, as I say here, in the proton NMR spectrum, multiple lines tell you the numbers of hydrogens on neighboring carbons. So you're going to be looking at your friends next to you. So in this case here, the multiplicity of this fragment of unknown structure, if you're looking at this hydrogen here and you're analyzing that, then you would see on the adjacent there's 3, and then on the adjacent there's 3. So you would have 6 total, like you'd have a sextet. In that case, it'd be a multiplet because you'd have 3 on the right, 3 on the left. If it was maybe carbon hydrogen, you could have doublet, because in that case you'd have a doublet from one side, doublet from the other side. It's a little bit easier to understand going forward when we look at broader examples, and then I'll kind of delve deeper into those multiplets. But just know that multiplicity is relative to the adjacent carbons and how many neighboring protons there are. So if there's no neighboring protons, you just have carbons attached and then that's it. Then singlet, that's it. You're only accounting for your proton specifically. No neighboring atoms, singlet. And then you go from there depending on how many that you have. So singlet is your base 0 in that case. The number of protons that you integrate, now this is relative to this specific, in a sense, carbon and proton that you're looking at, right? So the vertical distance on the integral of the signal at a given chemical shift, so remember the location, the ppm, is proportional to the peak area, and thus also to the number of protons having that chemical shift. And so this is related to integration in calculus. You have a shift, the area under that curve is equivalent to the integration of it. So integrating that area under the curve would be equivalent to the total number of protons under that curve. So if the total number of hydrogens is known, one can divide the total vertical integration by that number to get the vertical distance per hydrogen. So in theory, there are 6 hydrogens, so you might guess that this represents to 2 methyl groups in that instance. The 2 methyl groups, if they're symmetric, they will integrate together. That means that you would have a group of 3 hydrogens here, a group of 3 hydrogens here. They integrate together, and the peak that you would see would be 1 peak, total of 6 hydrogens integrated under that area. So integration is something that we perform using the machines already, or the software that we can integrate in. But reverse integration, like looking at an NMR and you see the integration, that can tell you information, so that way that you can, sum together, you can piece together the puzzle for unknown compounds. Or if you have a compound you made, you have a theory on that you think it's going to be at this location with this many hydrogens, you run your NMR, now you can nicely integrate it and confirm what you are taking your unknown sample, or your predicted sample that you created in lab up to the NMR machine. Now you know there should be, in that case, 6 hydrogens at 5 ppm, which is random, and you run the experiment, and then you see the 5 ppm. Oh, there's my spot. You integrate it. Nice, 6 hydrogens. Then you've confirmed your compound is correct. So that's an instance of where we would use proton NMR in a real life example. So the coupling constant, and this is a little bit more advanced and relevant in the sense that you can memorize some of these very well for certain specific functional groups, but it is better for the larger functional groups, so that way that you can look at that. The smaller ones can get kind of intertwined. So in this case, the effective magnetic field of the given nucleus is the sum of the imposed external magnet field. So think about magnets, how they add and subtract from each other with forces. So in this case, the hydrogen A and hydrogen B here, if both of them are moving that way, they add together in order to create a positive coupling constant, larger sum. However, if we have a positive A, negative B, then those two add together, plus minus, and then they create a coupling constant. And so the final takeaway from this is that we say the signal due to HA is split because of coupling to HB. So the magnitude of coupling, or the coupling constant, is measured in hertz, or 1 cycle per second. So the value of J, it can be seen here on table 13.2 down here. And my advice for this is to memorize a few of these, maybe some specific ones that are more applicable, because a lot of them overlap with each other. So the coupling constants can they can be helpful at the last determination to say, this is finally what I have. I've looked at the hydrogens. I've looked at the multiplicity. I've looked at, now I have only the thing left is coupling constant. Now, does it fit into my table? And then you can finally use that. I would not use coupling constants as the first thing to go to in order to analyze an NMR sheet, though. Okay, let's go back up. Okay, give me one moment. Okay, so in terms of coupling, protons with the same chemical shift will not show coupling. So protons on the same carbon that are geminal will show coupling if they have different chemical shifts. So in this instance, when we're talking about HA and HB, it's kind of like stereochemistry in the sense that this carbonyl is adjacent to the axial hydrogen, whereas this carbon is adjacent to the equatorial hydrogen. So make sure that if you're looking at it, you can see here, HA and HB are not equivalent. They'll have different chemical shifts and they will couple to each other, but they will be at different shifts because of the sort of location in space, because the NMR is pulsing frequencies at these hydrogens. So the multiplicity to return to this concept to understand it. So if a proton is coupled to more than one proton, the J values may or may not be equal. They're equal. The multiplicity of the signal for the first proton will be the number of hydrogens to which is coupled with that J value plus 1. So there's always that 1 adding into it. So the multiplicity here is the neighbors plus 1. This hydrogen, multiply it. There's just a bunch of adjacent carbon hydrogens. So not a very good sample. This one, okay. So this carbon, it has 3 hydrogens on it, but let's ignore that, right? Let's just say it's just 1 hydrogen. This is the main thing. We're looking at this. it says it's a triplet, right? So why is it a triplet? Because its neighbor has 2 hydrogens. So 2 hydrogens plus 1, now you have 3, triplet, right? So these hydrogen, triplet. Here, now this is where the doublet quartet part, we're going to understand it now. To the right, we have 3 hydrogens. Plus 1 is 4, quartet. Quartet on the right. Doublet, where does the doublet come from? The carbon next to it is a hydrogen, has 1 hydrogen. 1 plus 1 is 2, so you have a doublet, quartet. Okay, doublet on the left, quartet on the right, and you would see that on the on an NMR spectra. I kind of wish that they added one here, but that's okay. Let's keep going through the multiplicity so that way that we can get more examples. The hydrogen here, multiplet, not a very good example because, well, you can see here there's a ton of hydrogens around it, but that's not very descriptive. Let's look at this one. The only adjacent carbon to this methane, the CH3, will be this carbon. So this carbon has 1 hydrogen. That means 1 plus 1, 2, doublet. Because of that, what about this one? Same thing. The adjacent carbon, 1 hydrogen, 1 plus 1, 2. Doublet, doublet, they're both connected to that single carbon, single hydrogen. 1 plus 1 is 2. And that's the main theory of it. This is a great example. I love this example because it clearly maps out all the different ones. I wish they had a singlet here, but that's okay. A singlet would be very simple. You can actually, if you measured methane, it'd be a singlet. Because guess what? That carbon with 4 hydrogens on it, there's no neighboring carbons. You only have 1. You would see 1 sharp peak in methane because it would just be that 1 hydrogen you're measuring. There's no neighboring carbons. That's it. And again, if there are no protons attached to neighboring carbons, the proton signal will appear as a singlet. Okay, and so going forward, this is a good example. It's a little hard to follow because you're going to have to jump back and forth, but I'm going to slightly go through this. And I do definitely recommend to, as we did before in the IR spectra, since this is older information, look up some NMRs of common compounds, and then you'll be able to, look at the specific peaks and then find those specific protons attached to the specific carbons. And that way you'll understand not only the locations, but the multiplicity and then the integration factors. And then it'll all tie in together because they're all related. So, okay, for instance, and here we have these partial structures of this compound. And we're going to look at, I'm going to go ahead and skip to the next one because this one doesn't have an NMR. It just has just numbers here. And I would prefer to show you one with an NMR here. So in here, they give us the carbon. Well, we're not discussing carbons today. We're going to be discussing protons. So we have a triplet here with 6 hydrogens, multiplet here with 5, 1 hydrogen here, and then we have a doublet here with 2 hydrogens. So we count that there's 13 total protons connected. And so one important information that they're saying here is that when you use deuterated chloroform, it exchanges with the signal for the OH. So the actual the OH proton will disappear. Usually you won't really see alcohol protons because the deuterium will exchange with the hydrogen on your oxygens. So we can kind of ignore that. But however, if we look down from the data in table 13.1, and we'll jump down there in a second, we would see that methylene should have a signal shift of about 3.4 ppm. So looking down here at the 13.1, and we look here, methylene, now look here, the 2 circles methylene, at about 3.4, we should have a little peak for a methylene group. And if we look back up here, 3.5, we have here a doublet with 2 hydrogens. So here on the spectrum right here, 3.5, this is a great location to look. Then we can analyze that and see that from the integration to see the 2 hydrogens as well, this is a methylene group, so that which is a CH2, methylene CH2. And it's integrated for 2 protons, so we know for a fact that that's a methylene group here. Then secondly, the methyl groups, they stand out very easily within a proton NMR. And So they're very intense signals, 3 hydrogens each, and they can at most only have 2 protons on neighboring carbons. And so in this case, the methyl group's at about 0.9 ppm. We can see a 6 proton signal here, 6 hydrogens. See, 6 hydrogens here, and then that would be right here on this. So 6 hydrogens were integrated in this case. So you know it's 6 hydrogens. That's a very common spot for methyl groups. Again, you can refer to the table for how to locate what's there. But since we would see that, we know there's two methyl groups in that case, because it'd be 3 hydrogens, 2 methyl groups attached in that case at the 0.9 mark. So we're putting the puzzle pieces together. We're slowly taking each part. We know we have 1 methylene group. So here's our methylene. We know now we have 2 methyl groups because we see the 0.9, very important location to look at. And then, so now that we've done that, we have to put the puzzle pieces together. So here are the partial structures examples, right? Asymmetrical structure, here's this attached with our OH. The reason we know that there's an OH is because here, this is the structure C6H14O. We know additionally it has to be attached, one of them has to be attached to the oxygen. And so finally, if we put all the puzzle pieces together, we know we have the methylene group here. We have the methyl groups attached here, the very end. And then also we do have a single hydrogen. Now, which one was that? Looking back up, it's this multiplet, okay? 5 hydrogen multiplet. Here, you can see this would be attached within to here, and these are symmetrical as well. So symmetry on the carbon will make things overlap. So the methyl groups right here, overlapping, 6. The 6 groups, the methyl right there, overlapping. That's the 2 CH3s. So that's a total of 6. So we've taken that off now. Now, where are our CH2s? Well, let's see. We have here, looking up, we have the multiplet. So the multiplet's actually overlapping, and that is a very important thing to see here. 1.2 to 1.6, right? This group right here, 5 hydrogens. How do you do that? So 2 hydrogens here, 2 hydrogens there, and 1 here. So 5 hydrogens. That's why it's a multiplet, is because it's all in kind of a grouping and overlapping within that little region. So there's your 5. And then finally, your methylene group. So your methylene up here is showing alone. And that methylene was the 2 hydrogens. And then finally, you have your 1 hydrogen here at 1.9. And that 1 hydrogen would be, let's see, I think it'd have to be the alcohol here, because they're actually not clarifying that from the data. But regardless, the main thing that we can take from here would be the other groups here for the 2-2-1 making 5, the 3-3 making 6, and then this methylene giving the 2. So this is part of where I would say that going forward, to get more examples, definitely recommend either utilizing more resources on YouTube for NMR analysis, or looking up NMR spectrums of different sorts of functional groups and such, and that way you can see. And so in the sense of you're looking at rings, the way to analyze different things, you would see that there would be a different proton source for this versus if it was singly branched or if it's multiply branched. So in this case, ring C, you have your quaternary carbon, which you would never see protons from because it's quaternary attached. So there's no hydrogen there to analyze. But there's a hydrogen here on group B, and there's definitely a ton of hydrogens here on group A. So that's how you can analyze across separations of different NMR spectra, is by noting where should we look, what do our compounds look like, and how can we separate them from each other. And finally, this part here is going to be your procedure on how you're going to prepare spectrums. So it's going to be very short. Make sure to add in all the glassware, all of the required materials for this to perform your proton spectra. And honestly, I'm highly confused as to why there's a carbon-13 here, because we didn't discuss carbon-13 at all. This is one portion of the literature that I disagree with, but that's okay. These are going to be the spectra you're going to analyze, and you're going to draw after you've analyzed the material here. So please utilize the tables below in the section 13.1, so that way that you can utilize this. These problems, and make sure to listen to this very carefully, these problems here are going to be for your post-lab questions, okay? These are all the post-lab questions. Now, in this instance, the pre-lab, oops, I got that backwards. I'm sorry. So these ones are your pre-lab questions, okay? Scratch what I just said, my apologies. These are your pre-lab questions. So problem 1 here, problem 2, problem 3, problem 4, those are all your pre-lab questions, okay? Your post-lab questions are down here. These are the ones that you're gonna additionally analyze the same way that you did your pre-lab questions, and you're just gonna write them out. Each section is separated. So problem 3 is all, one group. Problem 2 is all one group, and then problem 1 is all one group, all one compound in a way. And make sure to look at these tables, 13.1, 13.2, and 13.3. Use those to target what functional groups that you have. And then finally, put the puzzle pieces together and then tackle the problem. So now I'm going to pause this share really quick, and we're going to jump over into our module. Let me save this one moment. So make sure, if you do have any questions regarding this, to go ahead and contact me over email, and provided that over to everyone on the first day of class. If I don't respond on email, feel free to contact me through Canvas. But let me go ahead and open up our module so that you can see exactly what will be due. One moment. Okay, now make sure to watch all of these videos. These will be very important to continue to clarify the information that you've learned here today with me. Additionally, please watch Dr. Britton's NMR training video. That will assist you in case you do need to run an NMR on campus in the future. If I'm still around, please make sure to contact me. I can assist you with any sort of NMRs that you might need for your lab. I'm very versed in running NMRs. And, of course, the pre-lab quiz, make sure that's already done. Then the post-lab notebook, come here and go ahead and submit it once you've completed that. And then over here, to get your samples, your unknown spectra, then they will be given here. These are the 3 unknown spectra that you need for your IR that you need to analyze, and then place what each functional group will be here. So you can also copy and paste that into your Word document for your lab. That's fine. That will not be plagiarism. Make sure, so for here, the IR pre-lab questions, once again, this is on page 14 of the lab manual that we just reviewed here. Questions 1 through 5. Then the IR post-lab questions from page 13, question 1 through 6. And then, let's see, make sure to review through these problems as well here for the NMR, 1 through 4, 1 through 3 for post-lab. And yeah, so basically, I mean, that's exactly it. Make sure just to do all the questions. This may be a little confusing because of they separate the questions, but if you maybe overlap your pre-lab and post-lab questions, that's okay. I won't take points off for that because I know that this older lab manual is a little bit confusing. Just complete every question that is given to you. If you by chance accidentally put your pre-lab and your post-lab questions area, I won't take points off for it. Just the number one thing is completion. So complete all of the questions, and please contact me via email if you need help with analyzing any of the data. I will not give out answers, but I will be able to assist you through the process and potentially provide you with any additional resources I may have to give you more clarification to certain locations for your IR spectra or NMR spectra. Otherwise, thank you for watching the video, and make sure to review all of the information inside of this module. As well, feel free to contact me once again if you need any assistance. Thanks for coming by, and I hope you have a great day.